In this episode, we wrap this portion of the course with a survey of specialized application ideas that appear across data and AI work, especially when problems do not fit neatly into classic regression or classification. Beginners often assume every problem should be solved by training a single model on a table of features, yet many real systems require structured reasoning about relationships, constraints, and sequences of decisions. In cloud security and cybersecurity environments, this reality shows up constantly because networks are connected systems, identities form relationship webs, and attackers often take multi-step paths rather than single isolated actions. To handle this, practitioners use tools like graphs to represent relationships, heuristics to make fast practical choices, greedy methods to build workable solutions step by step, and reinforcement learning to optimize decisions over time through feedback. The goal is not to master each topic deeply in one sitting, but to understand what each approach is, why it matters, and how to choose it responsibly without overclaiming. This is a survey, but it will still be taught with the same seriousness. Each concept will be explained clearly, connected to security realities, and framed with the misunderstandings that often trip up new learners. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Graphs are a specialized representation that becomes powerful whenever the relationships between entities are as important as the entities themselves. A graph is made of nodes, which represent entities like users, devices, services, or IP addresses, and edges, which represent relationships like logins, network connections, membership, or access permissions. The strength of graphs is that they capture structure that tables often hide, such as how one compromised account can reach many resources through privileged links, or how multiple devices connect to the same unusual endpoint. In cloud security, graphs can represent identity and access relationships, such as which roles grant which permissions and which resources those permissions touch. This can reveal risky privilege paths that are hard to see in flat logs, because the risk is in the chain, not in any single link. Beginners sometimes think graphs are only for social networks, but in security, almost everything is a network, including the infrastructure itself. A graph representation also supports different kinds of questions, like finding clusters of related entities, detecting central nodes that would be high impact if compromised, or tracing paths from an entry point to sensitive assets. When you adopt a graph view, you are acknowledging that relationships are first-class signals, and that changes what algorithms become meaningful. Working with graphs introduces its own challenges, because graphs can be huge, dynamic, and noisy, especially when built from logs. A graph built from network flow data can contain many transient edges, like short-lived connections, and without filtering it can become an unreadable hairball. This is where careful definition of nodes and edges matters, because you must decide what counts as a meaningful relationship, what time window defines an edge, and whether edges should have weights that represent frequency or volume. In security contexts, a single connection may be benign, while a pattern of repeated connections may be more informative, so edge weighting becomes part of meaning. Beginners sometimes assume building a graph automatically reveals insight, but a graph is only as useful as the way it is constructed. Another key issue is that graphs are time-dependent, because relationships change as users change roles, services are deployed, and attackers move, so the graph you analyze must be tied to a time window and versioned. If you ignore time, you can create impossible paths that were never present simultaneously, which can lead to overestimating risk. A thoughtful graph approach includes time awareness, filtering, and clear semantics, turning structure into a usable model rather than a confusing picture. Heuristics are simple rules or strategies that aim to produce good outcomes quickly without guaranteeing optimality, and they are everywhere in real systems because perfect optimization is often too slow or too costly. In cloud security, heuristics can include practical rules like prioritizing alerts with certain combinations of signals, limiting escalation to cases that cross multiple thresholds, or applying fixed risk weights to known high-impact actions. The key value of heuristics is that they are understandable, fast, and often reliable enough, especially when data is noisy and when the cost of complexity outweighs the benefit. Beginners sometimes assume heuristics are inferior to machine learning, but in many operational settings, heuristics are the safest starting point because they are transparent and easy to tune. Heuristics also provide a baseline that helps you evaluate whether a machine learning system is genuinely improving outcomes rather than adding complexity. The main risk is that heuristics can become outdated and brittle when the environment changes, and they can embed hidden biases if the rules reflect historical assumptions that no longer hold. Another risk is overconfidence, where people treat a heuristic as if it were an evidence-based model, forgetting it is a rule of thumb. Using heuristics responsibly means documenting them, monitoring their outcomes, and revisiting them as conditions change. Greedy methods are a class of strategies that build a solution step by step by making the best local choice available at each step. The word greedy can sound negative, but it is a technical description. The method grabs the locally best option without necessarily considering the global best outcome. Greedy methods are common because they are efficient and easy to implement, and in many problems they produce good solutions quickly. In security operations, greedy thinking shows up in tree-off, where you might always take the highest risk alert next, or in patch prioritization, where you might always remediate the most severe vulnerability first. The benefit is that you can act immediately and reduce risk quickly, which matters when time is limited. The risk is that greedy choices can miss better overall strategies, such as addressing a slightly lower severity issue that is widespread and therefore reduces more total risk, or choosing a sequence of actions that prevents multiple future incidents. Beginners sometimes confuse greedy with optimal, thinking that taking the best-looking next step must lead to the best overall result, but that is not always true. Greedy methods are tools for constrained environments, and their correctness depends on problem structure. Using them wisely means understanding when local improvements are likely to lead to global improvements and when they are likely to trap you. The relationship between heuristics and greedy methods is important because many heuristics are essentially greedy strategies with domain-informed scoring. For example, you might assign a risk score to each alert and then always take the highest score, which is a greedy selection based on a heuristic score. This can be effective, but the score must be aligned with real costs and benefits, or else the greedy approach will systematically prioritize the wrong things. In cloud security, a score that overweights noisy indicators can produce endless false positives, and greedy selection will then focus attention on noise, starving real issues of review time. Beginners can be tempted to add more signals to a heuristic score and assume the score becomes more accurate, but more signals can add more noise if they are not validated and calibrated. A safer approach is to evaluate heuristic scoring by measuring operational outcomes, like how many true issues are discovered per analyst hour and how quickly high-severity issues are resolved. If the greedy workflow improves those outcomes, it is doing its job, even if it is not mathematically optimal. If it worsens outcomes, the solution might be to adjust the heuristic, change the greedy rule, or adopt a more sophisticated approach. Recognizing greedy and heuristic structure helps you diagnose why an operational process is working or failing. It also helps you communicate clearly about what the system is doing, which reduces confusion and misplaced trust. Reinforcement learning is a specialized approach that fits situations where an agent takes actions over time, receives feedback, and learns a policy that improves long-term outcomes. Unlike supervised learning, where you learn from labeled examples, reinforcement learning learns from interaction. The agent tries actions, observes rewards or penalties, and updates its behavior to maximize cumulative reward. In security contexts, reinforcement learning can appear in automated response strategies, resource allocation, or adaptive defense mechanisms, where the system must choose actions under uncertainty and the consequences unfold over time. The idea sounds powerful because it resembles learning by experience, but it must be approached carefully because the learning process can be risky if exploration causes harmful actions. Beginners sometimes hear reinforcement learning and imagine a system that becomes automatically smart, but reinforcement learning depends heavily on how the environment is modeled, how rewards are defined, and whether exploration can be done safely. Reward definitions are especially critical because the agent will optimize what you measure, and if you measure the wrong thing, it will learn harmful behavior. For example, if the reward is minimizing alert volume, the agent might learn to suppress alerts rather than improve detection quality. Reinforcement learning is therefore not magic. It is optimization of behavior under a reward signal, with all the alignment challenges that implies. A key reinforcement learning concept is that actions can have delayed consequences, which makes the problem different from simple prediction tasks. In security operations, an action like locking an account might prevent an attack, but also disrupt a legitimate user, and the costs and benefits might become clear only later. Similarly, choosing to investigate one alert now might delay investigation of another alert, affecting outcomes in ways that unfold over time. Reinforcement learning frameworks handle this by considering cumulative reward, not just immediate reward, but that means you must define reward functions that capture long-term value. Beginners often define reward using easy-to-measure short-term signals, which can lead to unintended optimization that looks good on a dashboard but harms true risk management. Another challenge is that the environment can be non-stationary, meaning attackers adapt and systems change, which complicates learning because the policy learned last month may not be optimal today. This is why reinforcement learning in security is often applied cautiously, with strong constraints, simulations, and human oversight, rather than being used as an autonomous controller in high-stakes settings. The responsible framing is that reinforcement learning can suggest policies and automate low-risk decisions, while higher-risk decisions require more careful governance. Understanding delayed consequences helps you see why reinforcement learning is both promising and risky. Graphs, heuristics, greedy methods, and reinforcement learning also connect through the theme of structured decision-making, where you are not simply predicting outcomes, but choosing actions under constraints. Graph-based analysis can reveal paths and dependencies that influence which actions matter most, such as identifying a privilege path that should be cut to reduce risk. Heuristics can provide fast scoring rules that decide where to apply limited resources. Greedy methods can turn those scores into step-by-step action sequences that are operationally feasible. Reinforcement learning can, in principle, learn policies that outperform fixed greedy heuristics by considering long-term outcomes, but it requires careful reward design and safe exploration. In cloud security, you often need all of these at different times, because some problems require structural insight, some require fast tree-off, and some involve repeated decision cycles where learning over time might help. Beginners sometimes look for one best method, but the real skill is recognizing which tool fits the structure of the problem and the constraints of the environment. This is especially true when people and processes are involved, because the best theoretical policy is useless if it cannot be operated and trusted. The survey view helps you see these methods as complementary rather than competing. Evaluation and overclaiming control are especially important for specialized methods because the outputs can look sophisticated and therefore be granted too much authority. A graph analysis might produce a centrality score that suggests an entity is important, but that does not prove it is risky. It might simply be a common service account. A heuristic might prioritize a certain alert type, but that may reflect reporting bias rather than actual threat prevalence. A greedy method might resolve high-scored alerts quickly while missing a broader issue that spans many low-scored events. A reinforcement learning policy might maximize the chosen reward while harming unmeasured objectives, like user trust or compliance adherence. Beginners should learn to treat these outputs as evidence and guidance, not as proofs, and to validate them against operational outcomes. In cloud security, that validation includes monitoring for drift, checking bias across environments, and ensuring that decisions remain within compliance constraints. It also includes documenting assumptions, such as what the graph edges represent or what the heuristic score encodes, because those assumptions determine how results should be interpreted. Responsible use means you can explain why a method is appropriate, what it is optimizing, and what its known failure modes are. Overclaiming is avoided when you keep the method's claims tightly aligned with the evidence it can provide. As we close this survey, it helps to recognize the common thread. These specialized approaches exist because real systems have structure, constraints, and time-dependent decision cycles. Graphs capture relationships that matter for understanding paths, dependencies, and influence, which are central to cloud security risk. Heuristics and greedy methods provide practical, fast decision-making tools that can operate under limited resources and tight timelines, which is the daily reality of security operations. Reinforcement learning offers a framework for learning policies from feedback over time, but it introduces serious alignment and safety requirements, especially when actions affect people and systems. Choosing among these methods is not about picking the most advanced method, but about matching the method to what you know, what you can measure, and what you can safely operationalize. If you can articulate that matching process, you demonstrate that you have moved beyond treating AI as a collection of algorithms and toward treating it as disciplined decision support. That is the mindset that makes the CompTIA Data AI certification meaningful, and it is what will keep your future work grounded, safe, and useful.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.